Welcome back to The Explainer. Let's just dive right straight into part 2. In part 1, we talked about the basic shapes of process responses. Today, we're actually going to put exact mathematical numbers on those first-order response curves we covered. We're moving away from the abstract concept of a shape and getting right into the hardcore reality of measuring it. Okay, let's do a super quick recap of our 3 response shapes first. A first-order response is kind of like a single tank filling up. It's got this nice, smooth, predictable rise. Then you have your second-order response, which behaves a bit like a car's suspension hitting a bump, meaning it can actually overshoot before it settles down. And finally, the high-order response. This one is basically several storage elements chained together, which gives us the slow S-curve that starts out notoriously flat. Keep those shapes in the back of your mind as we go. All right, let's get into our next section, the time constant rule. So you really can't properly tune a controller by just guessing, right? You need a deliberate, exact measurement of how your process responds. And that brings us to the time constant, known mathematically as tau p. By definition, this is the time it takes for your process to complete exactly 63.2% of its remaining change. We usually measure this in minutes or seconds. It's essentially a speedometer for the process response. Now, if a system just kept changing at its absolute maximum initial rate, it would hit 100% of its target in exactly one time constant. But because the rate of change is constantly slowing down as it gets closer to the target, it naturally tapers off. Now, you might be wondering why 63.2%? I mean, it sounds super specific, right? Well, it's definitely not an arbitrary guess. It actually comes directly from the linear first-order differential equation that models these systems. When you solve that math for a step input, the result after one time period evaluates to 1 minus e to the power of -1. And mathematically, that equals exactly 0.632. So this is literally a mathematical law of physics for single capacity systems. Let's look at how this builds into an absolutely fantastic rule of thumb for when you're out in the field. After one time constant, you get that 63.2% we just talked about. Pass 2 time constants, and you're roughly 86% of the way there. 3 time constants, that gets you to 95%. And by the time you hit 4 time constants, a first-order process is roughly 98% settled. So for pretty much all practical industrial purposes, at 4 time constants, the response is just effectively complete. Which brings us to a major warning section: danger, high-order impatience. Okay, so smooth first-order math is great when you're dealing with a single tank or maybe a really fast flow loop. But applying it blindly is a massive trap. Treating a high-order S-curve like a fast first-order process is incredibly dangerous. See, a true first-order process starts responding immediately, even if it's overall a slow process. But a high-order reality, that includes this delayed, totally flat, dead phase before the S-curve even begins to climb. Because of that slow start to the naked eye, it literally looks like nothing is happening at all. And this right here perfectly illustrates the danger. Operators who don't recognize a high-order system will make an adjustment, see zero immediate movement on their trend, and just get impatient. So what do? They crank up the gain or aggressively open a valve, assuming the system is just stuck. But it's not stuck. That energy is just slowly making its way through multiple hidden lags. And when that delayed reaction finally hits, boom, all those aggressive adjustments hit the process at once, and it sends the loop into a violent, sometimes genuinely dangerous oscillation. Think of it like this. Texting a 5-person group chat is basically the ultimate high-order process. You send a message, and then nothing. Total crickets. That is your flat, dead phase. Your text is passing through multiple attention spans, lock screens, whatever. You might be tempted to fire off 5 more texts thinking nobody heard you. But then, all of a sudden, everyone replies at the exact same time and your phone completely blows up in this massive S-curve reaction. If you get impatient during that dead phase, you are just causing chaos. Let's look at a concrete, real-world example: the heat exchanger. Let's pull this out of the abstract for a second and look at an actual industrial application where these multiple lags stack up just like that group chat we talked about. A classic shell-and-tube heat exchanger almost always acts as a second or third-order process. Just think about the physical stages the energy has to travel through. First off, you've got fluid capacitance inside the tubes. The heat has to transfer through that fluid. Then you've got thermal capacitance in the metal of the tubes themselves. The metal literally has to heat up. And finally, you have the fluid capacitance on the shell side. You're stacking 3 completely separate lags right on top of each other. Because these 3 lags sit in series right between your control inputs and your temperature measurement, heat exchanger loops are just notoriously slow. They are the textbook perfect definition of a high-order S-curve. and they will easily, and I mean aggressively, overshoot if you impatiently tune them like they're some fast flow loop. You absolutely have to wait out that dead phase. All right, time for a loop tuning knowledge check. Let's pause for a super quick interactive moment to test your floor knowledge. Picture this scenario. You're out on the floor commissioning a brand new loop. You step test the controller, and you're just staring at a totally flat trend line on your screen for 40 long seconds. You're probably starting to wonder if the sensor's completely busted. But then, finally, it starts this slow S-curve climb. Based on everything we've covered today, how are you going to approach tuning this thing? The answer? You tune it slowly and you tune it very conservatively. That long 40-second flat start, followed by the S-curve, is the absolute unmistakable signature of a high-order process. It is not broken, it just has multiple lags stacked in series. If you apply aggressive tuning here, you are practically guaranteeing continuous cycling and oscillation the very second that delayed response finally shows up. Let's see what is coming up next. Okay, so you now possess the mathematical time constant formula, and you understand exactly why human impatience is so incredibly dangerous on high-order loops. In our next explainer, we are going to take a step back and firmly lock down the exact control loop vocabulary every single operator absolutely must know: PV, MV, OP, and set point. Because honestly, before you start twisting any dials, ask yourself, are you entirely sure you know the difference between manipulating an output and shifting a process variable? If you get those terms backwards, nothing else we cover is going to make sense. We'll find out next time.